and then times delta x, and we need our delta y in here. Okay, so all this between here and here is a sum that represents an integral over this strip, a y integral from the bottom to the top of a typical strip. As delta y approaches 0, this sum that we see here, this sum from j equals 1 to m of I, of your delta of xi star, yi star, delta xi squared, delta y, approaches, right at here, approaches an integral, and that integral is the integral of delta of xi star y times delta x I star squared dy, and I need my square on this term. Okay, so this expression in parentheses is going to approach this integral, so that this entire summation here becomes a summation from I equals 1 to n of y integrals times delta x. So I'm going to say that approaches, that this sum here, as delta y goes to 0, or as m of I goes to infinity, that this sum approaches the sum from I equals 1 to n of the integral of our, well, the integral we see here, the integral of delta of xi star y times delta xi star squared dy, and then times delta x. Now, what are our limits on this integral here? This integral represents a sum as delta y goes to 0 of a sum from j equals 1 to m of I, where m of I is an index. The index is the delta y's over a strip that runs from 0 to f of xi star. In other words, this sum represents what we get. This sum represents what we get when we partition the interval from 0 to f of xi star, so that the limits on the integral are the 0 and f of xi star. And that'll be the case here as well. Didn't space this very well. Let's put a little border there. Now, in the limiting process, remember it was delta y that went to 0, so that our y sub i's have been squeezed into infinitesimal intervals, and our y sub I stars become y. Our delta y becomes dy. Our delta x sub I squared isn't dependent in any way on y, so in fact this expression can be factored out of this integral. Could have been factored out of the sum previously, but let's go ahead and factor it out of the integral. So our integral becomes our sum becomes the sum of the integrals of f from 0 to f of xi star delta of xi star y dy times delta xi star squared delta x, and this integral xi star is going to remain constant. F of xi star is whatever it is. This integral then represents the average value of the density function along the vertical line x equal xi star from x equals 0 to x equals f of xi star multiplied by the length of that line segment. Okay, so I can say our inner integral is the average value of this function times the length of the interval. And this statement is just a direct consequence of the definition of average value for a function. Now if we take the limit as delta x approaches 0 of this sum, this approaches as delta x approaches 0 or n approaches infinity. This approaches an integral of an integral. The inner integral is 0 to f of xi delta of x y dy integrated, left off the x squared. Okay, fix that, times x squared dx. Another error here, this xi should have been an xi star, but since we've taken a limit as delta x goes to 0, that's been squeezed down to just an x. So is this, so this should just be an x. We shouldn't have the I there. I'll remove that in a minute, but let's think about what the limits are now on our x integral. This sum is a result of a partition of our original interval from 0 to 1. So this would be the interval from 0 to 1. So now we have the integral for our moment of inertia.